Jnanam Paramam Dhyayam. Knowledge is supreme.
So, in the last couple of lectures, we have discussed associated primes, support, and a primary decomposition of a module over an arbitrary commutative ring. Now, today we are going to discuss modules of finite length, and as usual, we will assume our ring is commutative and V be an A module. Now, to prepare, first I want to observe an interesting lemma which is also known as butterfly lemma of Zassenhaus, which says that if I have V and W are submodules of a module X, and let V prime and W prime be submodules of V and W respectively, then if you look at this quotient module V prime plus V intersection W and modulo V prime plus V intersection W prime, this is a submodule of the above because W prime is a submodule of W. This is isomorphic to W prime plus W intersection V modulo W prime plus W intersection V prime. So, we want to prove these modules are isomorphic. And why is it called a butterfly lemma? I have drawn a picture here. So this picture looks like a butterfly. That is why it is called a butterfly lemma. Okay, how does one prove this? So, by symmetry, see this, by symmetry it is enough to prove that this left hand side module is isomorphic to V intersection W modulo V prime intersection W plus V intersection W prime. Because if I prove this and then this equal to this, so that is very easy to see. Now, V intersection W is a submodule of V prime plus V intersection W. This is bigger one. Similarly, V prime intersection W plus V intersection W prime is a submodule of V prime plus V intersection W prime, because this one is contained here and this one is contained here. So, these are the submodules, and now we have therefore the map, we have a natural map. This is a submodule of this, this is a submodule of this. So, I take this going to this quotient module, and this one is because this is a submodule of this. So, we have a natural map, and this map is clearly surjective because any element here is coming from this one, because any element here modulo this, it is an element in V intersection W. So, that is coming from here. So, this map is clearly surjective. Now, therefore, we want to prove that this map is injective, but injective means the kernel should be contained in. So, remember here, this is the map, I want to prove this map is surjective. That means I want to prove that the kernel should be 0. That means what is the element in the kernel? The one which goes to 0 here. That means it is in the intersection of V intersection W intersection with this module. And if I prove that it is contained in this, that will prove the kernel is 0. But this is immediate. I have to prove this equality. Look, I have to prove this equality. So, if we take element in the left hand side, that is of the form x plus y, where x plus y is in this as well as in this, where that x is in V prime and y is in V intersection W prime. Then y is in W because W prime is a subset of W. So, y is in W, and therefore x plus y is in V prime intersection W plus V intersection W prime, because that's obvious. So that proves the kernel is 0, therefore the map is an isomorphism, and therefore it proves the Jasenows butterfly lemma. Now how am I going to use it? So first let us define, let us make a definition, a module V, and suppose I have a finite sequence of submodules decreasing, where it starts with V and ends with 0, and then the quotient modules, successive quotient modules, V1 by V0 by V1 and so on, Vn minus 1 by Vn, these are called quotients of this sequence. So we say that the sequence, the decreasing sequence of submodules and another one decreasing sequence of submodules, they are equivalent if the number of submodules are same, m equal to n, and there exists a permutation on n letters such that the quotients are isomorphic, the Vi by Vi plus 1 and V prime sigma I by V prime sigma I plus 1. If these quotients are isomorphic for all 0 to n minus 1, then we call these two decreasing sequence of submodules to be equivalent. Also, we say that the sequence of decreasing submodules which starts with V and ends with 0, there is a refinement of a sequence V0 to Vn to Vn, V0, the decreasing sequence of submodules, the lengths are different, but we say that this is a refinement of this if each Vi appears in this sequence V0 prime, V1 prime and so on. If it appears there somewhere, then we say that this is a refinement of this. In other words, we should be able to, this V prime sequence is obtained by inserting some more terms in the given sequence. Then we call it a refinement. So, that is what it is, that all these V's, Vi's appear in this sequence, then we call it a refinement. Okay, then now very important theorem of Schreier. Schreier's refinement theorem says that if I have a module and if I have two decreasing sequences which starts with 0 and ends at V, this is another one of submodules, they have the equivalent refinements. So the terms may not be the same here, but I can, both of them will be refinement of some bigger sequence. So we want to prove that these, we want to refine them both so that they become equivalent. Alright. So for I equal to, I am going to insert more terms in both the sequences. So let us define for I equal to 0 to n minus 1 and j equal to 0 to m. M is the second, m is the number of submodules in the second sequence. So Vij, that is Vi plus 1 plus Vi intersection Wj, and it is clear that Vij contains Vij plus 1 because the Wj's are decreasing. And what is Vi naught? Vi naught is by definition j is 0, so it is Vi plus 1 Vi intersection W naught, but W naught is whole V, so this is Vi only, and this is Vi plus 1, and that is decreasing, therefore it is Vi. So therefore, and what about Vim? Vim is Vi plus 1 by definition, Vi intersection Wm, but Wm is 0, so this is nothing, so this is Vim is Vi plus 1. This is true for all I from 0 to n minus 1 and j from 0 to m minus 1. So therefore we have V here, which is V00, which contains 0 1 and will go on decreasing till V0m, but V0m is V1 because I is 0, so this is V1, and now you start with V1 0. V1 0 is V1. So, these actually same term. Therefore, I wrote equality here. This again the same V1 1 goes on till V1 m, but V1 m is V2 and so on. So, we have such a decreasing sequence, and where this equality equal to this equal to this and so on, and this last one is Vn which is 0. So, therefore, this sequence which I have defined, it is a refinement of the sequence, it is a refinement of this given sequence of decreasing submodel V0 to Vn. Alright. And what are the quotients? Quotients are of the refinement Vij modulo Vi comma j plus 1. But these are the quotients. So, that is because we have noted Vim is Vi plus 1, which is Vi plus 1 0. So, this is the refinement. Now, similarly, I can now use the other sequence to define Vji equal to Wj plus 1 plus Wj intersection Vi, and this I do it for 0 to I equal to 0 to n and j equal to 0 to m minus 1. So, therefore, by the same way we get a refinement Wji. Now, j I is running from 0 to n minus 1 and j is running from 0 to m minus 1, and this is a refinement of this, and the successive quotients are Wji mod Wji Wj I plus 1. But now, we want to prove that these quotients are same. So, butterfly lemma will tell us, when I apply to V equal to Vi, W equal to Wj, V prime equal to Vi plus 1 and W prime equal to Wj plus 1, we will have this quotient. Just put on the definitions and apply butterfly lemma, then you will get this converted into this submodule, and where this is the quotient of the refinement serial. So, we have proved that these refinements have the same quotients. But now also we have to say that the permutations. So, because look at the pairs I comma j, I is varying from 1 to n minus 1 and j is varying from j to 0 to m minus 1, and j the other way, just interchange the coordinates. So, the numbers are same. These two indexing sets have the same cardinality, and the sigma is a permutation. When you switch the coordinates, this is a permutation. So, therefore, this is a permutation. So, therefore, we have proved the assertion that these two sequences have the common refinement. Okay, so this also I want to recall a definition of a simple module. Simple module means, first of all, the module is non-zero and the only submodules are 0 and V. For example, if you are over a field, if A, the base ring is a field, then K is simple K module. More generally, if you have a vector space, then vector space is simple if it is non-zero and the dimension should be 1. So, when the dimension is 1, it is non-zero. So, I do not have to say it is non-zero. So, vector space is simple if and only if the dimension is 1. Alright, now how do you test some modules are simple or not? We say the module is, we want to test a module is simple. We want to generalize this from the vector spaces. So, a module V is simple if and only V is isomorphic to as a module A by M, where M is a maximal ideal in A. Proof is very simple. So, suppose first assume V is simple, then we know V is non-zero, and if I take any non-zero element of V and take the submodule generated by X, that has to be the whole V because it is a non-zero and the only submodules are either 0 or the whole. So, therefore, V generated by X, and we have a model homomorphism F from A to V, just mapping A to A times X. This is clearly surjective because V is generated by X. Therefore, V will be isomorphic to A modulo the kernel of F, and the kernel of F has to be the maximal because A mod kernel of F is a simple module. It is isomorphic to V, therefore, it is a simple module. Therefore, it can't have any proper ideals. So, therefore, A mod kernel of F has to be a field. Therefore, M is a maximal ideal there. So, one way we have proved, the other way, if you have an ideal in the ring A, then the module A by A is simple if and only if A is a maximal ideal. That is, this is also very easy because this module is simple means it is non-zero first. So, therefore, A is a proper ideal and there is no other ideal in this residue class ring because the proper ideal of this ring will give you a proper submodule of A by A. So, that proves the proposition. Alright, if you have a module V and a submodule, then the quotient module is simple if and only if first of all U is a proper submodule and every submodule W in between either V U equal to W or W equal to V. So, this is like a maximal ideal. So, a submodule, the quotient module is simple if and only if there is no proper submodule in between the module V and the submodule U. Now, this allows us to make a definition. A decreasing sequence of submodules is called a composition series or Jordan-Holder series if all its quotients are simple submodules. That means you can't, first of all, that means these are proper inclusions and you can't insert anybody in between. That means you cannot make this sequence refine. So, that's what one has written. So, the composition series or Jordan-Holder series means in between any two terms there, we cannot insert any proper submodule for every I. Equivalently, this given decreasing sequence of submodules has no proper refinement, and in this case the natural number n, that is called the length of the Jordan-Holder series. So, the next theorem is Jordan-Holder theorem, which says that any two composition series of a module are equivalent. That means in particular they have the same number of terms. So, that means in particular they have the same lengths. This is very important theorem. It was proved for the groups first, the abelian groups first. That is because Jordan was studying Galois theory and therefore, it was very important to consider abelian groups and Jordan-Holder series like that. More generally also one considers such a series for arbitrary groups, but you have to assume that in the decreasing sequence of subgroups, each one is normal in the next one and so on, because then the quotients will make sense. Okay, the Jordan-Holder theorem is clear from Chayes refinement theorem, because once you have a composition series, you cannot refine any more, and therefore it has to be refinement of itself only. So, therefore, if I take two composition series, Chayes refinement theorem says that they have a common refinement, but each one is a refinement of itself. So, therefore, these any two composition series are equivalent, and in particular they have the same number of terms and the same quotients also. So, that is Jordan-Holder theorem. So, remember that the Chayes refinement theorem is more general and it was proved later than the Jordan-Holder theorem. Actually, but now the proofs, I have used the theorem which was proved later because it was more general. Anyway, so now we can make a definition. An A module V which has a composition series, that is called a module of finite length, and in this case the length of that composition series of V have the same length. This is well defined because we have just proved in a Jordan-Holder theorem that any two have the same length. So, this length is well defined, and that length we call that is the length of V, and it is denoted by LAV. So, length of V as a module. Okay, note that when will the length be 0? That means the Jordan-Holder series, it has a composition series and that has only one term, namely 0. So, V is 0, that is equivalent to saying V is 0. When will the length be equal to 1? That means V has to be simple, because the composition series starts with V and ends with 0, and there can't be any more terms because all the terms are not there, because length is 1 and therefore the quotient is simple. So, that means V by 0 is simple, so that is V is simple. So, if a module does not have composition series, then we will say that module V is not of finite length, and in that case we will put length of V to be infinity. Alright, now we have to make a criterion. How do we decide whether a module has a composition series or not? And now we are discussing that. The corollaries which I deduce from Jordan-Holder theorem, that will lead to some answers. Alright, so suppose I have a module of finite length, then any strictly decreasing sequence of submodules can be refined to composition series, but the assumption is V should have finite length. Okay. In particular, the length of every such sequence is at most the length of the module V. This should be V. So, this is also immediate from the refinement theorem, because given this sequence I will keep refining it, and already I know there is a composition series for V that exists because V is of finite length, and this I by inserting more and more terms I refine and make it as a composition series. But then these two composition series have the same length, and therefore this M will be at most length of V, because length of V is by definition length of a composition series. Now, this one, the next proposition will allow us to compare the lengths of a module and its submodule and the quotient module. So, if V is a submodule of V, U is a submodule of V, then length of U as a module and length of V by U as a module, that is same thing as length of V. Alright. So, this formula is even true for when the length is not finite. Okay. So, that is the next statement is, if a length of V is finite and U is a proper submodule of V, then length of U is strictly smaller than length of V, because we can increase the composition series at least by 1. This is a triviality. So, length of V is finite and U is non-zero, then length of the quotient module is strictly less than length of V. If length of U is finite and length of V by U is also finite, then length of V is also finite. This is also easy because length is finite, so U has a composition series, and this is finite, so it has a composition series. So, lift the elements in the composition series and you will get a composition series. So, I will not prove this proposition, it is left as an exercise. Alright. So, similarly, so we can deduce immediately from this, if I have a short exact sequence of A modules, V prime to V double prime, this is a short exact sequence, means it's here the kernel of this map equal to the image of this map is injective, and this map is surjective. That is the meaning of the fact that this sequence is an exact sequence of submodule A modules. Now, the assertion is if V is of finite length, V is finite length if and only if this middle one is finite length, if and only if the outer ones also are of finite length, and in that case the length is additive. That means length of the middle one is length of V prime plus length of V double prime. Alright, this is because you can think this is a submodule of this and V double prime is a quotient module of this. So, the earlier proposition will tell you this length is additive. So, this is also, see, this property can be described by saying that length is an additive function on the category of A modules. Okay, more general version of this corollary is if you have a long exact sequence like this which has many terms. So, that means you have the maps and at each stage kernel equal to the image. Kernel of the later map is the image of the earlier map. Then you call such a sequence to be exact sequence of A modules. Suppose in this sequence of modules all but one of them is suppose that all but one of the Vi are of finite length. That means only Vi may not be finite length and all others are finite length. Then the assertion is the remaining Vi is also finite length, and in that case we have alternating sums of the lengths is 0. So, this assertion is trivial for n less equal to 1 because there is only either 0 term or only one term. In that case the assertion is this is isomorphism. So, this equal to this, therefore, so this is assertion is clear for n equal to less equal to n minus 1. So, I am going to prove the assertion by induction on n. Therefore, we assume first n is at least 2 and I am going to put this kernel of, so we know kernel of f1 equal to image of f2 and I am going to call it u. Then we can break this long exact sequence into two exact sequences, namely this u is the kernel of this f1. So, therefore, we have the short exact sequence and now this u is also the image of f2. So, I will forget v1 and put it at u and therefore, this sequence is clearly exact. So, these are two exact sequences. Now, this length as this I can apply the induction and therefore, the assertion follows by the above corollary because for this alternating sum is 0 and for this I will replace the length of u by coming from here alternating sum again. So, therefore, the assertion is clear by induction on n and we will continue after the next break. So, that we will connect this concept of finite length with the support and associated prime ideals and also relations with the Noetherian and Artinian models. So, thank you.